So in this problem, we're required to solve for all possible values of t that would make this equation true. So right off the bat, we have cosine of 2t. And recall from the double angle identities, we're able to expand this three different ways. I'm going to pick the expansion that only has cosine in it, which is the 2 cosine squared of t minus 1. The reason I'm picking this is because the other ones have sine in them, and it would be easy for this equation to just have one trig function. We don't need both cosine and sine. That would make things more difficult. So I picked the one with cosine, and this would clean up nicely. So I'm going to rewrite this equation again. Cosine of 2t, that expanded into this 2 cosine squared of t minus 1. That's cosine of 2t. I just expanded that. So we have that plus 2 cosine squared of t is equal to 0. Now, I'm going to combine like terms. I'm going to combine this 2 cosine squared of t with the other one. And that's going to give us 4 cosine squared of t minus 1 is equal to 0. Now we want to isolate the trig term. So I'm going to add 1 on both sides. So we get the trig function by itself. So we have 4 cosine squared of t is equal to positive 1. Again, I want to isolate the trig function, so I'm going to divide both sides by 4. And that would give us cosine squared of t is equal to 1/4. Now the last step, or not the last step, we want to get rid of this squared. So to do that, I'm going to square root both sides. Now we're going to have cosine of t is equal to plus or minus the square root of 1/4. Now the square root of 1/4 is 1/2. So cosine of t is equal to plus or minus 1/2. So technically we have two equations out. We have cosine of t is equal to positive 1/2, and we have the negative version. Cosine of t is equal to negative 1/2. So let's look at both of these. Let's look at the unit circle. So recall that cosine is the x value. So for positive 1/2, it would be at these points. And if you recall at the unit circle, these points are pi over 3 and 5 pi over 3. So again, this is the x coordinate of the point. It's 1/2. So cosine of pi over 3 is 1/2, and cosine of 5 pi over 3 is 1/2 as well. Now for let me just color code this. So yeah, for 1/2 we have pi over 3 and 5 pi over 3. And now for negative 1/2, it's going to be at these points. And this is 2 pi over 3, and this is 4 pi over 3. So the cosine is negative 1/2 at 2 pi over 3 and 4 pi over 3 only. So these seem to be our solutions. We have t is equal to pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. You can also express these in degrees, but we usually express them in radians. So these seem to be our only 4 answers. But if you think about it, what about 7 pi over 3? Since 7 pi over 3 is equivalent to pi over 3, Remember, 7 pi over 3 is equal to 1 whole revolution, 2 pi, plus pi over 3. So really, we have 7 pi over 3. This is 8 pi over 3. So we have infinitely many different radian measures that have the same cosine that have the same cosine value, because again, 7 pi pi over 3 is equivalent to 7 pi over 3. That's also equivalent to 13 pi over 3, and the list goes on. So we need to find a way to express those different versions of this angle measure. So if we think about it, if we take pi over 3, let's just look at pi over 3. I'm going to erase these so they're out of the way. If we take pi over 3 and we add pi, that's going to give us 4 pi over 3. That's one of our solutions. And then if we add pi again to 4 pi over 3, that would give us 7 pi over 3. To make this easier, this is essentially adding pi is the same as adding 3 pi over 3, if you want to look at it that way. So 4 pi over 3 plus 3 pi over 3 would give us 7 pi over 3. And then adding pi to that would give us 10 pi over 3. And then, but it would just keep on rotating between these 2 points, this one and this one. So it looks like no matter how many times we add pi, we're still going to land on these 2 valid solution points. So we can say that t is equal to pi over 3. And remember, we can add pi as many times as we want, and then we're still going to get valid answers. So to condense that, let's say for any integer n, we can add pi that many times and we would get our solution. So we can say let n be any integer. Okay. So that's one half. The other half, let me erase these so they're out of the way. So now let's look at this part, the 2 pi over 3. Again, if we add pi plus pi, we're going to end up with 5 pi over 3. And then if we add pi again, we're going to end up back at 2 pi over 3, also known as 8 pi over 3. And then we can keep on adding pi infinitely many times. We're still going to be looping back and forth between these 2 points. So now we found another way to express these 2 points, since this answer represents these 2 points looping infinitely forever. And now we can also say that t is equal to 2 pi over 3, and then again we can add pi infinitely many times, and then it would still give us a valid solution. So I'm going to say plus n pi for any integer n, and that represents the points in the green. So these may be valid solutions, but that doesn't account for all of the different solutions, because again, 7 pi over 3, 8 pi over 3, those could be solutions to this problem. So to account for all of those, we're just going to say for any integer n, we can keep on adding pi to these specific radian measures, and then those all would be valid answers. So technically, all of our valid answers would be in an infinitely large set. But this is all the information we need.